Welcome back to the deep dive. Today we are attempting something truly ambitious.
I'd say so.
We're trying to map the mind of a man so astonishingly comprehensive in his thinking that the world, well, it just sort of stopped producing his type after he was gone.
We're talking about Gottfried Wilhelm Leibniz.
Exactly. And we're diving deep into his life, his philosophy, his mathematics, all of it.
That's the German polymath, born in 1646. And when I say polymath, I mean it's almost an understatement.
Right.
He was a top-tier mathematician, a groundbreaking philosopher, a scientist, a diplomat, a historian, a legal scholar.
Right.
All at the same time.
The sheer scale of it is what's so hard to grasp, and that's why he gets that unique and really imposing title, the last universal genius.
And that title, it sounds romantic, doesn't it? But it's not just a nice phrase.
No, it points to a real historical shift. You could argue that after Leibniz, human knowledge it splintered.
It did. The Industrial Revolution, the rise of specialization, it became impossible for one person to credibly claim mastery over all the major fields. He was kind of the end of that Renaissance ideal.
So that's what makes this deep dive so interesting, but also, really challenging, the state of his work.
Oh, it's a mess. It's a glorious, chaotic mess.
How much are we talking about?
We're dealing with a legacy spread across an astonishing 15,000 letters.
Yeah.
And then 40,000 other items.
40,000.
40,000. Most of it in Latin, French, or German, and a huge portion of it was never even published in his lifetime.
Okay, so let's set out our mission here. We're looking at the co-creator of calculus, the father of the binary code that is literally powering the device you're listening on right now.
A foundational figure in rationalist philosophy, right up there with Descartes and Spinoza.
So our job is to navigate all of that, this incredible breadth, and focus on the connections. I mean, how did his very abstract philosophical ideas end up influencing the architecture of our modern digital world?
That's the key. We have to see the symmetry in his vision. We'll get into the big breakthroughs like the calculus feud.
Oh, we have to talk about the feud.
Of course. And the monads, those strange, tiny, fundamental units of existence that make up his universe.
And we can't avoid his most famous, or maybe infamous idea.
The idea that we live in the best of all possible worlds.
Yeah, right. So our mission is to provide you, the listener, with a map to an entire intellectual continent. One man's attempt to systematize, well, everything. To understand how a mind like that even comes into being, we have to start at the beginning. His formative years in Leipzig.
He was born in 1646, and his father was a professor of moral philosophy at the university. So, a very academic household.
But that stable world didn't last long.
No. His father died when Leibniz was only 6 years old.
And that loss, as tragic as it was, became this incredible intellectual opportunity.
He really did, because the young boy inherited his father's extensive personal library, and crucially, he was given free access to it at age 7.
And this wasn't, a collection of children's books?
Not at all. This was a serious academic library full of advanced philosophy, theology, history, things that were way beyond what a 7-year-old was supposed to be reading.
So he just teaches himself. He becomes this self-guided learner, devouring scholarship that his peers wouldn't see for another decade.
Exactly. And the results were, prodigious. By age 12, he was completely fluent in Latin.
The language of all scholarship at the time.
Right. And he wasn't just reading it, he was thinking in it. There's this fantastic story from when he was 13.
Go on.
He composed 300 hexameters of really complex Latin verse in a single morning for a school event.
Wow.
He shows this stunning ability not just to consume knowledge, but to structure it, to express it really, really rapidly.
So his path seems set for academia. He enrolls at Leipzig University at just 14.
Unbelievable, isn't it? He gets his BA and then his MA in philosophy. And his master's thesis, it actually contained the seeds of what would later become his famous monad theory.
The idea of these unique, simple substances.
Right. And then he moves on to law, which in that era was the fastest track to, court service and real political influence.
But then he hits a wall. A rejection in 1666 that turns out to be a really critical moment.
It is. Leipzig University denies his application for a doctorate in law.
Why? Was his work not good enough?
No, not at all. The consensus is it was almost certainly just his age. He was only 20.
Too young for the old guard.
The faculty probably just thought this kid is too young for such a high degree. But Leibniz, instead of, waiting around, he pivots instantly.
He just leaves.
He leaves. He moves to the University of Altdorf, submits a new thesis, and gets his doctorate that same year in November 1666.
And here's the kicker. They offer him a job. a permanent academic post, a safe, prestigious career.
And he turns it down flat.
Why?
He said his thoughts were turned in an entirely different direction. He didn't want to just teach what was already known. He wanted to apply his knowledge to build new systems.
And he saw that future in the world of diplomacy and politics, not in the university.
Absolutely. Yeah. Which leads to his, let's say, his very unusual first job.
This is the Alchemical Society, right?
Yes. He gets a job as a salaried secretary to an alchemical society in Nuremberg. And he later admitted he knew, and I quote, fairly little about the subject at that time.
So he basically faked it till he made it.
He did, and it shows his audacity. He used the position to get noticed, and it worked. He quickly found a real patron, Johann Christian von Boinberg.
And that's his entry into the big leagues.
That's it. Now he's assisting with redrafting the legal code for the Electorate of Mainz. He's operating at a high level of statecraft.
Which brings us to this incredibly bold geopolitical plan he cooked up, the Egyptian plan. It sounds like something out of a thriller.
It's a masterclass in 17th century strategic thinking. The biggest threat to the German states at the time was Louis XIV of France.
The Sun King.
Exactly, just constantly expanding. And the German lands were fragmented, still recovering from the 30 Years' War. Leibniz's idea was brilliantly simple: create a diversion. He drafted a proposal to convince Louis XIV to invade Egypt.
Seriously?
Oh, yes. The plan was framed as this noble, civilizing Christian mission, a new crusade. It would bring France immense wealth, and it was a stepping stone to conquering the Dutch East Indies. But the real goal
was to send the massive French army far, far away from Germany.
Precisely. It was a pure realpolitik disguised as a crusade.
And did it work?
Well, it got him a trip to Paris in 1672 for high-level talks. The plan itself eventually fizzled out because of the Franco-Dutch War, but that trip to Paris, that changed everything for Leibniz.
This 4-year period from 72 to 76, this was the real intellectual catalyst, wasn't it?
It was a crucible. In Paris, he meets the great Dutch physicist and mathematician Christian Huygens.
And Leibniz, for all his genius, realized he had a major gap in his knowledge.
A huge gap. He knew his own advanced math and physics were not up to par, so Huygens becomes his mentor. And that period of intense study is what leads him directly to his greatest mathematical discovery. Calculus. And at the same time, he's visiting London, showing off a calculating machine he designed to the Royal Society, and they make him a member.
But then his patrons in Mainz die, and he needs a new job.
Right. So he accepts an offer from the powerful House of Brunswick in Hanover in 1676.
And even getting to his new post was an intellectual tour.
It really was. Yeah. On his way, he stops in The Hague. First, he meets Antony van Leeuwenhoek, the guy who had just discovered microorganisms.
Wow.
And then, even more importantly, he spends several intense days in conversation with the philosopher Baruch Spinoza.
Spinoza, who had just finished his masterpiece, The Ethics.
Imagine being a fly on the wall for those conversations. Right. The leading empirical scientist and the most radical rationalist philosopher of the age back to back.
So he finally settles in Hanover, and he's there for the rest of his life, serving as historian, political advisor, ducal librarian.
And this is where we see the universal genius start to clash with, the mundane realities of working for a royal court.
You're talking about the History Project?
The Endless History Project. He was commissioned to write a history of the House of Brunswick all the way back to Charlemagne. The goal was purely political, to boost the dynasty's prestige. He never finished it.
And it became a symbol of his famous procrastination. Why couldn't he just get it done?
Because his idea of done was completely different from his patrons. They wanted a quick, popular book, maybe 3 years' work. Leibniz insisted on a meticulously researched, comprehensive scientific history based on primary sources from archives all over Europe.
So he saw history as a systematic science, not just storytelling?
Exactly. He published 3 huge volumes of source materials, but the actual narrative history. It was still incomplete when he died 40 years later.
And that gap between the perfect systematic vision and the messy reality, we see it in his engineering too, right? With the windmills.
Oh, the windmill project, a perfect example. He championed this hugely ambitious plan to use windmills to drain water from the mines in the Harz Mountains. Very theoretical, very clever.
But in practice,
a total failure. The machinery kept breaking down, the economics were all wrong, and they had to shut the whole thing down by 1685. It cost a fortune, and it was a major personal embarrassment for him.
But despite these practical failures, his diplomatic brain was still working at the highest level, especially when it came to the British throne.
This is where he was so influential. He played a key role in the negotiations for the British Act of Settlement in 1701.
Which was the law that basically said the next monarch had to be a Protestant.
Right. And it specifically designated the Electress Sophia's line, the Brunswicks, his employers, as the heirs to the British throne. It was a brilliant political maneuver.
And when Queen Anne died in 1714, the elector's son, George, sailed to England and became King George III.
And Leibniz, the procrastinating historian, was one of the key architects who put a new dynasty on the most powerful throne in Europe.
Okay, so that's the diplomat. But now we have to get into the area where Leibniz's work is truly immortal, mathematics. And you can't talk about Leibniz and math without starting with calculus.
And, of course, Isaac Newton.
The great calculus controversy. One of the most famous priority disputes in the entire history of science.
It poisoned the relationship between British and continental mathematics for a century. The bottom line is, they both invented it, independently.
How close was the timing on this?
Well, Newton started his work on what he called fluxions a bit earlier, in the 1660s. But Newton was famously secretive, very slow to publish.
And Leibniz?
According to his notebooks from his time in Paris, his big breakthrough happened on a specific day, November 11th, 1675. That's when he first used integral calculus to find the area under a curve.
And he published his work in 1684, which was before Newton's Principia came out in 87.
Correct. But the real lasting victory for Leibniz wasn't about who was first. It was about the notation.
The language he used to write it down. His system is the one we all learn in school today.
It is. Newton used this sort of dot notation above the letter, which was fine for him, but less flexible. Leibniz introduced the integral sign, that long S shape.
From the Latin word summa, for sum.
Exactly. And he gave us the did for differentials, which gives you expressions like did x. His notation was just better. It was clearer, it showed the relationship between the parts, and it made the rules of calculus much easier to use.
So this superior system should have been a great thing for science, but instead it just fuels this nasty personal feud.
It got very ugly, and it really overshadowed the last years of Leibniz's life. The first real shot was fired in 1708 when a follower of Newton named John Keill publicly accused Leibniz of plagiarism.
Just flat out said he stole it.
Flat out. Suggested he'd seen some of Newton's unpublished papers and just copied the ideas.
And the British scientific establishment didn't exactly handle this impartially.
Not even close. The Royal Society launched a formal investigation. The problem was Newton was the president of the Royal Society at the time.
So he's investigating himself, basically.
He essentially ran the whole thing. Modern historians have shown he manipulated the committee and even helped write the final report, which, surprise, surprise, found Leibniz guilty. It was an institutional hit job.
But today, historians are unanimous that Leibniz is innocent, right? They were two different paths to the same mountaintop.
Absolutely. And their approaches were fundamentally different. In fact, Leibniz's method, using these things called infinitesimals, was actually vindicated in the 20th century. Plus, his other contributions are immense. We still call the product rule Leibniz's law. He gave us the Leibniz integral rule. He even came up with a formula for pi.
So leaving calculus aside, we get to something even more prophetic.
Yeah.
The modern binary number system, base 2. The zeros and ones that are the absolute foundation of all digital computing.
This is probably his single greatest claim to being a visionary. I mean, he didn't invent the concept of binary, but he's the one who standardized it, who saw its true logical power. For him, 0, 1 weren't just numbers. They were the essence of creation itself.
And he found this incredible confirmation of his idea from a very unexpected source.
From China. This is where his universalism is just so cool. He was fascinated by Chinese civilization and corresponded with Jesuit missionaries in Beijing.
And they sent him something?
They sent him a diagram of the 64 hexagrams from the ancient Chinese text, the I Ching.
And he sees a pattern.
He sees the pattern. He realizes that these hexagrams, which are made of combinations of solid and broken lines, correspond perfectly to the binary numbers from 0000000 to 111111.
Wow.
For him, this was profound proof. It showed that his rational, logical binary system wasn't just his idea. It was a universal truth, a language of creation that was secretly encoded in ancient Chinese philosophy.
So he uses this ancient Eastern wisdom to validate his Western rationalist project. He even tried to share this with the Emperor of China.
He did. He sent his binary system to the Kanki emperor, basically arguing that the Christian story of creation making everything from nothing or zero and God or one was mathematically proven and was even present in their own ancient texts. A remarkable bit of mathematical diplomacy.
And this logical insight flows directly into his work on machines. He builds the stepped reckoner.
This was a huge leap forward for calculators. Pascal's earlier machine could only add and subtract. Leibniz's machine could do all four basic operations: adding, subtracting, multiplying, and dividing.
And the key was this invention called the stepped drum.
That was the big innovation, a cylinder with teeth of different lengths that could perform multiplication through repeated addition. It was brilliant.
But the technology of the day couldn't quite keep up with the theory.
That's the story of so much of his applied work. The machine was mechanically finicky. It struggled with the carry operation, which is crucial for accuracy. Again, the mathematical theory was perfect, but the 17th century gears and metalwork were messy.
But the truly mind-blowing leap, the one that anticipates our entire digital age, came a few years later in 1679.
Yes, this is when he's thinking about binary, and he has this vision of a new kind of calculating machine, one where the binary numbers wouldn't be gears, but physical objects.
He imagined marbles.
He imagined marbles, representing zeros and ones, dropping through channels, and the path of those marbles will be controlled by a kind of perforated plate.
A rudimentary form of punched cards.
Exactly. It's the fundamental concept of a programmable computer, 2 centuries before Charles Babbage and Ada Lovelace.
That's unbelievable.
It is. If you just replace his marbles and gravity with electrons and voltage registers, you have the basic architecture of a modern computer. He's the first true computer scientist, the first information theorist.
And his mind just kept organizing things. He was also laying the groundwork for fields like linear algebra and topology.
He had this incredible knack for seeing structure. He was the first person to arrange the coefficients of linear equations into arrays, what we now call matrices.
To solve systems of equations.
Right. He developed the theory of determinants, which is a way to check if a system has unique solution. We still call one method the Leibniz formula for determinants.
And even in geometry, he was hinting at really futuristic ideas like fractals.
Well, he coined the term analysis status, which is what we now call topology, the study of shapes and their properties under deformation. The fractal thing is a bit more metaphysical.
What did he say?
He gave this definition of a straight line as a curve, any part of which is similar to the whole.
Wait, a part that's similar to the whole?
That's the core concept of self-similarity. It's the defining feature of fractal geometry. It just shows how his brain would leap from a practical calculation to the most abstract, philosophical definition of reality itself.
Okay, we've seen Leibniz the mathematician, which is staggering enough. But his philosophical system is just as ambitious, placing him in the top tier with Descartes and Spinoza.
He's a leading figure of 17th century rationalism. The core belief is that you can arrive at real substantive knowledge about the world just through pure reason, starting from first principles.
His whole system is built on 7 of these principles, but let's focus on the 3 big ones, the ones that really run his universe. The first is the principle of sufficient reason.
This sounds pretty simple on the surface, almost obvious.
Everything must have a reason.
Exactly. Nothing happens by chance. Everything that exists or happens or is true must have a reason that is, at least in principle, understandable.
And this isn't just a general observation for him, it's a foundational tool.
It's the engine of his metaphysics. It's how he proves the existence of God. The world we see, he says, is contingent. It could have been otherwise. Therefore, there must be an ultimate necessary reason for its existence, a reason that is not contingent on anything else. And that, for him, is God.
So it's his way of guaranteeing that the universe is fundamentally intelligible, not arbitrary.
Right. If you deny it, he'd say, you're embracing chaos and reason becomes impossible.
Okay, the second pillar is the identity of indiscernibles. This one also seems to be about enforcing a kind of strict order.
It is. It's a very powerful rule of logic. It states that 2 distinct things cannot have all their properties in common.
So if you have 2 objects, and every single thing you can say about object A is also true of object B,
then they are not 2 objects. They are one and the same object. This was super important for him to guarantee that every single thing in his universe was absolutely unique.
But this one ran into some trouble later on, didn't it? Especially in physics.
It did. In the quantum world, you have particles like electrons that are considered to be truly fundamentally indistinguishable from one another, which seems to violate this principle. But for Leibniz's system, it was essential.
Which brings us to the third and maybe most famous and complex idea: pre-established harmony. This was his answer to the mind-body problem from Descartes.
Right. Descartes couldn't figure out how the non-physical mind could interact with the physical body. Leibniz's solution is radical. He just gets rid of interaction altogether.
So substances don't act on each other at all?
Not directly, no. In his view, every substance, your mind, your body, a rock, a planet, is completely independent and self-contained.
Then how does anything happen? I mean, how does the world seem so coherent? If I decide to lift my arm, it lifts.
Because, he argues, God is like a divine clockmaker. At the moment of creation, he pre-programmed the intrinsic nature of every single substance, every monad.
So they're all running on their own internal program.
Perfectly synchronized. He uses the analogy of two perfectly built clocks. They both chime at the exact same moment, not because one caused the other to chime, but because they were built in perfect harmony from the beginning.
So to use the example of a dropping glass, the impact of the floor doesn't cause the glass to shatter.
No. The glass was pre-programmed with an internal instruction, at this exact moment, shatter. And the floor was programmed with the instruction, at this exact moment, feel an impact. Their actions are synchronous, but not causal.
That is a wild idea, and it leads us straight to the fundamental building blocks of his universe: the monads.
The monads, which he describes in his monadology, they are the ultimate simple substances of reality, the final irreducible units.
But if they're the building blocks, what are they made of? Are they physical?
This is the key. They are not physical at all. They have no material properties, no spatial extension, no parts. If they had parts, they could be divided, and he needed them to be the ultimate indivisible reality.
So what are they?
They're best thought of as non-physical centers of force, or maybe even better, as metaphysical points of perception, packets of information and potential.
Okay, wait. If these monads aren't physical, how do they combine to create the very physical world we live in? Tables, chairs, planets. Is he just saying the physical world isn't real?
In a way, yes. For Leibniz, all space, matter, and motion are what he calls phenomena. They are appearances that arise from the collective perceptions of these underlying non-material monads. Matter is just what a collection of monads looks like from the outside.
And since they don't interact, each one is completely independent. And yet, you said earlier, he calls them little mirrors of the universe.
That's his beautiful phrase for it. Each monad reflects the entire cosmos from its own unique point of view. It's a universe of infinite independent perspectives, all held together in perfect pre-established harmony by God, the monis monadum.
The monad of monads. And this perfect, harmonious creation brings us to the idea that got him into the most trouble:
His theodicy, his philosophical optimism.
In 1710, he publishes the Theodicy, and it's his attempt to solve the ancient problem of evil.
Right. How can an all-powerful, all-knowing, all-good God allow evil and suffering to exist?
And his answer is that this world we live in is, in a qualified sense, the best possible world that God could have created. That just sounds so hard to swallow.
It sounds incredibly naive, especially to modern ears. But his argument is purely logical. God, being perfect, has perfect knowledge, power, and will. He knows every possible world that could exist. He has the power to create any of them. And being perfectly good, he would only choose to create the best one.
Therefore, this one must be the best one, flaws and all. The flaws must be necessary.
Exactly. He says God permits what he calls moral evil sin and physical evil pain and suffering because they are unavoidable consequences of something more fundamental, metaphysical evil.
And what's metaphysical evil?
It's just imperfection. The simple fact that anything created cannot be as perfect as its creator. Only God is perfect. So any created world must, by definition, be limited and contain some degree of imperfection, which then manifests as the suffering we see.
But this very logical, very abstract defense of God ran into a very real, very brutal wall.
It did. In 1755, there was the Great Lisbon earthquake, a massive catastrophe that destroyed a major European city and killed tens of thousands of people on a holy day.
And that event was the perfect ammunition for Voltaire.
Perfect. Voltaire published his satirical masterpiece, Candide, in 1759, and it just mercilessly mocks Leibnizian optimism.
Through the character of Professor Pangloss,
Who, in the middle of the most horrific disasters, keeps repeating the mantra, All is for the best in the best of all possible worlds.
And Voltaire's book was so witty and so popular that it completely shaped the public perception of Leibniz for centuries. He became synonymous with this naive, out-of-touch philosopher.
What's so amazing about Leibniz is that these huge, abstract philosophical systems weren't just intellectual exercises for him. They were the foundation for his ultimate practical goal.
The universal mechanical calculation of truth.
Exactly. He genuinely believed that most human arguments could be settled not by debate, but by calculation, which leads to his famous quote.
Let us calculate without further ado to see who is right.
That quote captures his entire ambition. And to achieve it, he dreamed up two tools, the characteristica universalis and the calculus ratiocinnator.
Okay, let's break those down. The characteristica universalis, the universal characteristic. What was this supposed to be?
It was a plan for a perfectly logical, universal symbolic language. His idea was that all complex thoughts are just combinations of a small number of simple, fundamental concepts. The goal was to create an alphabet of human thought by assigning a unique symbol to each of these fundamental concepts.
So instead of the fuzzy word love, you'd have a precise symbol built from the combination of symbols for, I don't know, desire, benevolence, commitment.
Precisely. And he even had a mathematical idea for how to do it, using prime numbers. You could assign a prime number to each core concept. Then any complex idea would be the product of those primes, giving it a unique numerical signature.
That's an incredible anticipation of Gödel numbering, reducing language to unique numbers. So if the characteristica is the language, the calculus ratiocinnator is the engine.
It's the calculus of reasoning. It was meant to be a formal set of rules, an algebra of thought, that would allow you to manipulate these symbols mechanically.
So two people in a dispute would translate their arguments into this universal language.
And then just run the calculation. The argument that was logically consistent and free of contradiction would be proven true, mechanically.
It's the dream of ending all conflict through pure logic. It's really the theoretical basis for modern symbolic logic and even the concept of computation itself.
A system that would just abolish ambiguity. It's the ultimate rationalist dream.
And this drive to systematize everything also led him to challenge the biggest scientific figure of his day, Isaac Newton, on an even more fundamental level than calculus.
Oh, their rivalry went deep. It was about the very nature of space and time. Newton believed that space and time were absolute. They were like a fixed, empty container that things exist inside of.
The substantivalist view.
Right. Leibniz argued for a completely relational view. He said space and time aren't things in themselves. Space is just the system of relations between objects, and time is just the order of events.
And in the long run, who came out on top in that debate?
Well, for centuries, Newton's view dominated. But then Einstein came along. General relativity, with its idea of space-time being warped by mass and energy, is much, much closer to Leibniz's relational view.
He also had a different idea about force, something he called vis viva.
Vis viva, or living force. He defined it as mass times velocity squared, which is basically twice the modern definition of kinetic energy.
And Newton focused on momentum, which is mass times velocity.
Exactly. And this wasn't just a technical detail. Leibniz was arguing that his vis viva was the quantity that was truly conserved in the universe, which was a pioneering step toward the modern concept of the conservation of energy.
So in the end, they were both right in a way. Momentum is conserved, and so is energy.
Yes, but Leibniz deserves huge credit for being the first to really champion the idea of energy conservation as a fundamental principle of physics.
And he applied the same systematic thinking to the human mind. He's now seen as a kind of underappreciated pioneer of psychology.
His work here comes straight from another of his core principles. Natura non facit saltus. Nature does not make leaps.
There are no sudden jumps. Everything is a continuum.
Right, so he couldn't accept a sudden leap from unfeeling matter to a fully conscious mind. There had to be a gradient.
So he proposed the idea of petites perceptions, little perceptions.
Small, unnoticed perceptions. His analogy was the sound of the ocean. You hear the roar of the surf, but you don't consciously perceive the sound of each individual tiny wave hitting the shore. But your mind is still processing all of them.
And these tiny, unnoticed perceptions add up until they cross a threshold into awareness.
Exactly. They transition into what he called apperception, which is full, self-aware consciousness. And this idea, this continuum of perception, is a direct precursor to the concept of the unconscious mind. He basically argued that for consciousness to work the way it does, there has to be a vast amount of mental activity happening below the surface of our awareness.
And this drive to organize wasn't just for science and philosophy. He was constantly trying to create applied systems for society.
In everything.
Mm.
In law, he wanted to create a rational science of right. In religion, he spent enormous energy trying to reconcile the Catholic and Lutheran churches, believing logic could heal the schism of the Reformation.
And his political ideas were centuries ahead of their time.
Absolutely. He proposed a kind of European confederation governed by a council or senate. It's a remarkable anticipation of the European Union.
And in social science,
He advocated for a public health authority, tax reforms, a national insurance program. Everywhere he looked, he saw chaos that could be fixed with a rational system. Yeah.
which brings us to his day job for 40 years, his work as a librarian.
He's considered one of the founders of modern library science. When he took over the Ducal Library in Hanover, it was a mess. He immediately set out to systematize it.
Wow.
He created a proper alphabetical author catalog, which was a big step. But more importantly, he developed a subject classification system. Broad categories like theology, jurisprudence, philosophy, history, imposing a rational order on the physical collection of books.
And he even had an idea for a kind of proto-internet for information sharing.
So visionary. He called on publishers across Europe to start distributing standardized abstracts of all their new books. The idea was to create a central, searchable index of all new knowledge being produced.
That proposal failed then, but the concept.
Is the foundation of every modern library cataloging system, like the Library of Congress system. For him, the library wasn't just a warehouse for books. It was the database for his universal science. It's just incredible, then, that when Leibniz died in Hanover in 1716, his end was marked by such neglect. It's a real historical irony.
Despite everything he'd done, especially for the House of Brunswick.
Neither the newly crowned King George III, the man Leibniz had helped put on the British throne, nor anyone from the Royal Society in London, where he was a member for life, even bothered to show up for his funeral.
That's just astonishing. The man who co-invented calculus, whose notation we all use, who designed the political architecture for the British Crown, who founded the Berlin Academy of Sciences, he was just buried in obscurity.
It's worse than that. His grave went completely unmarked for 50 years.
And his public reputation at the time was at an all-time low.
It was in the gutter. He was seen as the loser in the calculus feud, a plagiarist. And then his entire philosophical system was basically reduced to a joke by Voltaire's Candide.
So for decades after his death, the greatest mind of the 17th century was remembered as a philosophical simpleton. After all that work, what does it say about the scientific community of that era?
It says that at that moment, nationalism and loyalty trumped universal truth. The fight between Newton and Leibniz created this huge intellectual schism between Britain and the continent. And for a long time, the English-speaking world just decided to collectively erase Leibniz's contributions.
So when did things start to turn around? When did the recovery begin?
It was a very slow process. It started to bed in 1765 when his new essays on human understanding were finally published. But the real rehabilitation didn't happen until the 20th century.
With philosophers like Bertrand Russell?
Exactly. Analytic philosophers like Russell and Louis Couturat went back and looked at his work on logic and metaphysics, and they were blown away. They realized how deeply he had anticipated the foundations of symbolic logic and formal systems.
They saw the genius behind the universal characteristic and understood that it prefigured the very logic that makes computers work.
And so today, his recognition is finally where it should be. His manuscripts are a UNESCO Memory of the World Treasure. The biggest science prize in Germany is the Leibniz Prize. He's finally appreciated for the entire universal architecture of thought he tried to build.
So what does this all mean for us? For you, the listener, who are the inheritors of his digital and rationalist dreams, we started this deep dive saying Leibniz was dedicated to finding universal systems, systems that could reduce any argument to a pure calculation.
His ultimate dream. The perfected characteristica universalis and the calculus ratiocinator.
Right. So you could just say, let us calculate without further ado to see who is right.
The ultimate rationalist fantasy. The end of messy human conflict through clean, mechanized logic.
So here's the final thought. Given the immense complexities of our world modern geopolitics, the ethical minefields of AI, the chaos of misinformation on social media, does Leibniz's ultimate dream still offer us a pathway to rational resolution? Or does his ambition fundamentally ignore the truly incalculable, the non-rational parts of human nature, the passions, the biases, the metaphysical evil, that maybe can't be reduced to a calculation? That is the thought worth carrying with you.
A fitting challenge from the last man who tried to know everything.
We hope you've enjoyed this deep dive into the extraordinary life and legacy of Gottfried Wilhelm Leibniz. Until next time, keep digging.